Hi, welcome to Learner's Academy. Today we're diving into something that sounds fancy, but is actually pretty straightforward once you get the hang of it. The laws of exponents. Now, if you've ever Googled this topic or studied in math book, you've probably seen a list of equations that look like they belong in a secret math society. But don't worry, we're going to break it all down, one step at a time. By the end of this, you'll not only understand these laws, but also see why they make sense. And if you're not totally comfortable with the basics of exponents yet, no worries. Check out our previous videos to get the basics of exponents. Ready? Let's go. First, let's talk about what an exponent is. An exponent tells you how many times a number, also known as the base, is multiplied by itself. For example, x to the power 3, or x cubed, means the base x is multiplied by itself 3 times. X times x times x. Got it? Good. All right, let's start with the first two laws on our list. These are the foundation, and if you've watched our video on exponents and roots in algebra, these should look familiar. But if you haven't, no worries. I'll explain everything step by step. Now, the first law says that anything raised to the first power is just itself. So, x to the first power is just x. It might seem obvious, but let's think about why this makes sense. If an exponent tells you how many times to multiply a number by itself, then x to the first power means you're multiplying x by itself exactly once. And multiplying something by itself once is just the number itself. So, x to the first power equals x. Simple, right? Now, let's move on to the second law. This one says that anything raised to the power 0 is 1. So, x to the 0 power equals 1. You might be thinking, how does that work? If exponents are about repeated multiplication, how can you multiply something 0 times and get 1? This one might feel a little weird at first, but let's break it down. Think about exponents as a pattern. Let's start with x to the power 3. That's x multiplied by itself 3 times. By now, we also know that x to the power 2 is x times x, and x to the power 1 is just x. Now, what's x to the power 0? If you look at the pattern, each time you reduce the exponent by 1, you're essentially dividing the previous exponent by x. So, following the pattern, x to the power 0 is x to the power 1 divided by x. It can also be written as x divided by x, which is 1. So, x to the power 0 equals 1. This might still feel a little abstract, so let's use a real number to make it clearer. Let's say x is 5. So, 5 to the power 3 is 125. 5 to the power 2 is 25. 5 to the power 1 is 5. And to find 5 to the power 0, we follow the pattern. 5 to the power 1 divided by 5, which is equal to 1. Easy, right? To sum it up, x to the power 1 is x and x to the power 0 is 1. These two laws might seem simple, but they're the building blocks for everything else we're going to talk about today. Therefore, make sure you've got these down before we move on. Now, what if we have a negative exponent, like x to the power of -1, or -2, or even -3? We know exponents are about repeated multiplication, but how do you multiply number by itself negative number of times? You can't. That's where the next law comes in. It tells us that x to the negative power n is the same as 1 divided by x to the power n. Let's see, how does it make sense? A negative exponent is essentially the inverse of its positive counterpart. Since positive exponents means multiplication of numbers by itself, therefore negative exponents mean repeated division. For example, x to the power -1 means 1 divided by x, and x to the power -2 is 1 divided by x divided by x. This can be extended for other negative exponents also. But mathematicians prefer to express negative exponents in fraction form, where 1 is divided by the same number of x's multiplied together. But since those multiplied x's are all on the bottom of the fraction. You're actually dividing by all of them. Let's test it with actual number, with negative exponent, 2 to the power negative 3. If we write it as repeated division, it's 1 divided by 2, divided by 2, divided by 2. By using calculator, we can get the answer as 0.125. Now, if we write it in fraction form, as the law of negative power tells us, it's 1 over 2 cubed, which is 1 over 8, or 0.125. Whether you write it as a pattern of repeated division or in fraction form, like our inverse law shows, you get the same answer. All right, let's move on to the next law. It tells us what happens when you raise x to a power and then raise to another power. Here you can see that x to the power m is grouped in parentheses, and it is then raised to another power, n. It's a nesting situation, just like Russian nesting dolls. For example, what if you have x squared cubed, which means the entire x squared term is raised to the third power? Well, our law tells us that we can simplify that by multiplying the exponents together. It is just like x, power of mn, which means m times n. Therefore, it can be written as x to the power of 2 times 3, which is 6. Want to see how it works? Let's break it down. The x squared term is raised to the power 3. Therefore, we can write it as x squared multiplied 3 times. Each of x squared can also be simplified as x times x. As you can see, we have 6x multiplied to itself. Therefore, it is x to the power 6. See, the law works perfectly fine. If you have a number raised to a power, and that's all raised to another power, you can just multiply the two exponents together to simplify it. This law even works with negative exponents. For example, x squared to the negative power 3. This can be described as x to the power of 2 raised to the power negative 3. Now, by applying the rule, x power 2 times negative 3 is x to the power negative 6. To see if that's true, we'll need to use the law we just learned about negative exponents and rewrite this as 1 over x squared to the power positive 3. That simplifies to 1 over x squared times x squared times x squared, which in turn simplifies to 1 over 6 x's being multiplied together. And that all checks out, because 1 over x to the power 6 would be the same as x to the power negative 6. Now, let's tackle the next two laws together because they're like two sides of the same coin. These laws show us how to multiply and divide expressions that have the same base. It's important for the bases to be same to apply this law, because we couldn't simplify them if the bases were different. The first law says that if we have the base x with exponent m being multiplied by the same base x with exponent n, then we can combine them simply by adding the exponents together. The second law says that if we have the base x with exponent m being divided by the same base x with exponent n, then we can combine them simply by subtracting the exponents. Let's do some examples. 2 to the power 3 times. 2 to the power 4. Does that fit the pattern of the law we studied? Yep, the base of both expressions is the same, but they happen to have different exponents. The law would still work if the exponents were the same. Why does this work? Well, 2 to the power 3 is 2 times 2 times 2, and 2 to the power 4 is shown here. When you multiply them together, you're essentially multiplying 7 2's, which is 2 to the power 7. So, adding the exponents makes sense. The second law is about division. If you're dividing two expressions with the same base, you subtract the exponents. For example, 4 to the power 3 divided by 4 to the power 2 is 4 to the power of 3 minus 2, which is 4 to the power 1, or just 4. But is that right? To see, let's write the expression out in expanded form. On the top of our division problem, we have 4 to the power 3, which is 4 times 4 times 4. And on the bottom, we have 4 to the power 2, which is 4 times 4. Since all the bases are the same, they form pairs of common factors on the top and bottom that can be canceled out. This 4 over 4 cancels and this 4 over 4 cancels. And what do we end up with? Well, there's only one 4 left on the top, and all the factors on the bottom canceled out, which leaves 1, since there's always a factor of 1. See, it really did work. And we got the answer 4. Let's try using this law again with the expression x to the power of 2 over x to the power of 4. Our law says that we can simplify it by subtracting the bottom exponent from the top, right? But in this case, we will get a negative exponent because the bottom exponent is bigger than the top, as we know that 2 minus 4 would be negative 2. So according to our law, this expression should be equal to x to the negative 2. Let's try writing it out in expanded form to see if that's true. On the top, x to the power 2 would be the same as 2 x's multiplied together. And on the bottom, x to the power 4 would be the same as 4 x's multiplied together. Once again, we see that there are pairs of common factors that we can cancel, 2 pairs to be precise. And when we cancel them all, we're left with a 1 on the top, because there's always a factor of 1, and only 2 x's multiplied together on the bottom. If we recombine these 2 x's, we get 1 over x squared. And if you remember the law we learned earlier about negative exponents, you'll see that 1 over x squared is exactly the same as x to the power of negative 2. See, the laws really do work. Finally, we've got the last 2 laws, and they're pretty straightforward. These laws are about distributing exponents across multiplication or division. These laws look kind of similar to the last pair. Just like before, the first one involves multiplication, and the second one involves division. However, if you have noticed, previously, the bases were same and the exponents were different. But now, the bases are different, but the exponents are the same. Kind of exact opposite situation from the last pair of laws. It turns out that these laws aren't about simplifying exponents. They're about how you can distribute, or undistribute, a common exponent to different bases. The first law shows this group, x times y, that's being raised to the power of m. And it says that you can rewrite it as x to the power m times y to the power m. In other words, you can distribute the exponent to each factor in the group. And the second law shows the group x divided by y that's being raised to the power of n. And it says that you can rewrite it as x to the power n divided by y to the power n. In other words, you can distribute the exponent to each part of the fraction. These laws would work in reverse too, and you could undistribute the exponents if they're the same. Here are 2 expressions that will help you see why you can distribute or undistribute exponents like our laws show. In the first expression, we have the quantity x times y squared. That's the same as x times y times x times y. As per commutative property, we can rearrange these factors as x times y times y. This can be simplified into x squared times y squared. So that got verified. In the second expression, we have the quantity x over y squared. It can be written as x over y times x over y. Now to multiply these fractions, we just multiply the numerators and multiply the denominators, which give us x times x over y times y. And this can be written as x squared over y squared. So that one checks out too. All right, that's it for the laws of exponents. You've got the tools, you've got the knowledge, and now it's time to put it into practice. Remember, these laws aren't just random rules. They're based on how exponents really work. So don't just memorize them, understand them. And the best way to do that is practice. Thanks for hanging out with me today at Learners Academy. Until next time, keep solving those puzzles.